And then I'm going to share the screen. Hope everybody's having a good day today. I'm going to share Canvas. So I guess I need to show you where to find the midterm today, which is probably everybody's central focus, maybe. All right, so there's our course homepage. Lecture videos are all sitting right there if you want to see any of them. Homework solutions, and right now you don't see homework 7, but by the end of the day today, homework 7 will be posted there, and if that might be a resource that you use to do the midterm. Okay, we'll keep scrolling down. The subject of the midterm is scattering and chapter 3 formalism. So scattering from chapter 2, there are the solutions to the worksheets from those two tutorials. In the formalism, I posted all the solutions to all the tutorials. I guess there were 5 of them, right? 6 of them. 1, 2, 3, 4, 5, 6 of them. And so all 6 solutions are posted. Like I said, homework 7 solutions will be posted here shortly. And as you see, I'm scrolling down. It's not active yet. That's why you won't see it until I hit these 2 buttons, and I'll do that right after class. That makes them active. And there it is right there. 3 problems. It, I think, takes up, I gave you all kinds of space to work the problems out on. But if you need more space, feel free to just grab a sheet of paper and answer them. And then, of course, in the assignments place, that's where you'll upload it. It's a file upload, PDFs preferred, but whatever you use, upload it right there. Midterm exam 2. Okay. I am going to have regular office hours today to talk about homework 7. If there are any questions, I do recognize there's probably some overlap between questions on homework 7 and something you might find on the midterm exam. Hey, that's just a great question then if that happens, right? That means somebody's asking a question that's important because it was both on the homework and it might turn out to be on the midterm exam. So that's it. Shouldn't be, I don't think it's overly difficult if you've done the scattering tutorials and the homework on scattering, homework 6, I guess, and you've done the worksheets, the tutorials from the formalism, and the homework from the formalism, homework 7, I think you should be in pretty good shape. And if everybody will make little mistakes multiplying matrices out, you should have some tests that allow you to see, is that matrix the right matrix? Is that eigenvalue normalized when I check it out? If you find that they're not, we'll go back and find you made a little math error somewhere and fix it. And that way you'll get full credit. But in most cases, I think you should know the answer makes sense. And if it doesn't, that means you're making some kind of math issue. Any questions on the homework right now? I like I said, I will have normal office hours. I think 3:30 has been working pretty well. That keeps going generally till around 5 o'clock. So if you can't be there right at 3:30, feel free to stop by anytime up to about 5. At about 5, I start to cut it off because I got to go eat dinner, at least get dinner ready. Okay. Last chance for any questions. Everybody hearing me? Somebody answer. Jacob, answer up. You good to go?
I can hear you. I'm good.
All right, excellent. All right, so we're going to talk. I have 2 days. We're going to talk a little bit about angular momentum. I have 2 days scheduled for it. I didn't want to get too far into it today because the tutorial dealing with angular momentum won't be due till next Wednesday. And so I don't think too many people are going to look at it, but I will be going over the first page and a half of a 3-page tutorial. I won't do every problem, but I'll do similar problems. And of course, you'll have to do it again, due next Wednesday. I also have all day Friday after you turn in the midterm to finish up angular momentum. It's about, I think, a day and a half's topic. And of course, I scheduled 2 days. Hopefully we won't go too long, give you some time to work on the midterm or think about the midterm or ask questions about any of the midterm or procedures or anything like that. And so I'm going to stop sharing my Canvas page, and I'm going to shift over to sharing PowerPoint. And yep, it's got a box around it, and I can bring us on over, and we'll put those away so that they don't bother us in our video. And I want to take you back to chapter 2 when we were thinking about commutators for probably the very first time. And I suspect before I saw it in a quantum mechanics class, this is a mathematical operation with these square brackets. And I'd never seen it before until quantum mechanics. And of course, now you should know that that's defined as being what, x times px, the momentum with respect to x. And of course, I'm meaning that minus I h bar derivative with respect to x minus the other way, px times x. That's what this means. And just as a refresher of what the significance is, you can see if two operations commute, like normal multiplication of two numbers, the difference between these two things is 0. And then we say they commute. But there are operations where they don't commute. Okay, if it's 0, they commute. But if it's not 0, like the case of momentum and position, you get a number that's non-zero. Happens to be a complex number because the square root of -1's in there. But then there is a difference between x and p and x. So this commutator that we talk about is the degree to which two operators either commute or don't. And so we played with that one. And the question for the morning, because we've transitioned since chapter 2 into thinking about things in 3D. And if this is how you'd express the momentum operator for x components of momentum, because everybody should remember momentum's a vector. You've all had advanced mechanics. That should be no big deal to understand. It shouldn't surprise you that the y component of momentum then simply shifts to taking now not a full derivative. I changed the d from the block d for just a total derivative to a partial derivative. Right? I've changed to that. And so that's, I guess, the one thing I had to do when we went into 3 dimensions. And then if I want the y component of momentum, it hopefully makes sense that I just take the derivative with respect to y as opposed to taking it with respect to x. And similarly for the z component, I take the derivative with respect to z. It's still minus I h bar up front. And so the question, I guess, you might ask is, does the x operator commute with the y momentum operator? Or the y position, x, y position commute with the momentum in the x direction? Or take in the z, does the z position commute with the x momentum operator, for example? And I hope you realize that I could have taken this to y and py, and that would have been IH bar as well. And if I'd had z and then pz, it still would have been IH bar. But what about when I have two different directions for the operator as compared to the momentum? All right, and so let's just check. Our procedure is always to put in a test function, right? And this was actually on the last midterm, as I recall. Won't be on this one, but you have to take these two guys just like we talked about. And so I guess the first one is x times minus I h bar derivative of f with respect to y, because that's what the y momentum operator says, right, on this test function. And then I subtract off, like we said, the operator minus I h bar derivative with respect to y, and then x times the function, because now the x is on the other side of the operator. And as you probably realized from your multivariable calculus, that's just a constant with respect to taking the derivative with respect to the y variable. So it could come right out front. And I hope this isn't a big surprise, but just proved very formally, I guess, because of that negative sign right there, and because it's subtracting off a negative sign makes that a positive. These two terms, once I bring that x out in front of the derivative, it's equal to 0. A kind of a succinct way of writing what we've just been talking about right here is, if I take a position, maybe I should call it a position vector. Your author doesn't bold it or put it in a vector symbol, but this just means r is equal to x and y and z, right? Normal Cartesian coordinates. Okay. If I take, this is the first one, this is the second one, this is the third one, and that's supposed to be a Z right there, but didn't come out real well there. That's a better looking Z with a component of momentum. Okay. Again, 1, 2, 3 would be the X component of momentum, the Y component of momentum, the Z component of momentum. If I'm doing the commutation between those position and momentum's operators, okay, it's going to be IH bar. And here comes our buddy, the direct delta again. The only time it wouldn't be zero is when I and J are the same, as we talked about over here. Okay, those are the cases where it's not zero. If any time this is an X and a Y, or a Y and a Z, or any of the combinations I was trying off the top of my head to come up with, and there's a whole bunch of them, well, that would make the Kronecker delta be zero, because I and J wouldn't be the same. And so the commutator of those things would be zero. We would say they would commute. I hope you realize it, because I don't think we've ever proved it, but following this along, X and Y, or X and Z, or Y and Z, they commute, right? Just check. I mean, come on over to here. Just think about it for a second. Is XY minus YX equal to zero? And the answer is, of course they are. They're just numbers, they're positions. And so there's no function of taking a derivative like you have right here, where you have to make a decision. Does switching the order cause you to have to do a chain rule or not, or product rule, I guess, or not? And the answer with position is, of course, no. And then these two guys are both just derivatives in integral calculus and differential calculus, in multivariable calculus. Did you ever find that the order of taking a derivative, or for that matter, the order of taking an integral, mattered? And so since these are just taking derivatives, the order doesn't matter. So we would expect these two guys to commute. And you can prove that if you want to yourself more formally, but I think I've beaten this horse enough. Okay. So what I called back in chapter 2, the canonical commutation relationship. When somebody says that about some mathematical relationship, when they call it canonical, that means it's kind of something you should have as it's like knowing trig identity, cosine squared plus sine squared is equal to 1. It's something you should just kind of know. So the commutation of the position and momentum operators is IH bar. Okay, now we've made it a little more detailed in 3 dimensions. It's IH bar, but only when the position and the momentum component are the same direction. Okay, and everything else is zero. Everything else commutes. All right, I want to review vector cross product multiplication. And the only reason I did that is because I was doing torque on a dipole in my 112 class. And, I know you guys have all been through Kaiser's advanced mechanics. Yeah, with, I guess, what book did you use? Yeah, I don't remember. I've got it on my bookshelf. You used a kind of advanced mechanics book, which had a lot of math in it. And I bet you did cross product over and over again. But I still found that people in 112 weren't very familiar with it. Found when I taught other classes, advanced physics classes, it's not something that everybody works with a lot. And so it is worth just a second to go over. And so I've got 2 vectors in 3 dimensions, and I kept it in Cartesian. And I just want to remind everybody, I cross J, I cross I, J cross J, and K cross K are all 0. And there's a cyclic nature to the other unit vectors. I cross J is K, J cross K is I. And as long as you maintain the order, and what I mean by that, I've seen the mathematicians do it's a mnemonic basically of this. If I'm going this way around the circle, okay, I always get a positive result. Okay, so that's why if I go K crossed I get J, right? And that's what I wrote right here at the end. On the other hand, if you go the opposite direction, if you go this way around, the resulting unit vector is the missing unit vector, but it's negative. So I cross J, J cross I, for example, would be minus K. And I cross K would be minus J. It's the last one I wrote here. And then, of course, the other one is that guy. So those are negative. And that's just it's a fact. It's the way we define right-hand coordinate systems, and cross product follows from that. And I write this out just to remind everybody, if you have a technique, why that technique works. Okay. And so I looked at these 2 vectors, A here and B, and I multiplied them out, hopefully in a very sequential fashion, because I said, well, I got to take this component and multiply it by each of those three guys. And so that's what I did right there. And then I got to take the next component, multiply by each of the components of B, and then I got to take the Z component of A and multiply by each of the components of B. And hopefully you can see there's 3, 6, 9 terms there, which I wrote here on this line. Okay. Now here's the deal, I guess. Anytime I had I cross I, J cross J, and K cross K in this, like right there, there's a coefficient, I got I cross I. That term right there goes to 0, as does the J cross J, as does the K cross K. And I'm left out of the 9 terms from expanding using just a distributive property. I'm just left with these 6. And that's really the answer to how to do cross product. And this is the cool part for me. If you need to look, and let's just look at like the I direction, okay? And all I did was use these guys, right? To simplify, say, I cross J became K, right? So that's why there's a term right there, AX BY times K, because that's that term right here. And I wrote it right there. And this guy right here, I cross K, would be minus J, AZ, B. That's that term right there. And I just did that for all 6 terms. I guess just the cool part. If you write out this determinant, and we've been playing with determinants now, and so everybody should be fairly familiar with this, that actually gives you all 6 terms in exactly the right order you need them if you can correctly evaluate that determinant. But that's why it works. And I think it's never a bad thing to remind ourselves of that. Okay, there's our vectors. There's the answer. One of my colleagues at the Naval Academy used to call this it's really just a mnemonic to remind you, because who the heck can remember this bottom line right here for cross product? Okay, and I think that's one way to do cross product. This is more what I'm doing in my 112 class. We find the magnitude because we take the magnitude of A, magnitude of B, and multiply by the sine of the angle in between them, because that's how cross product is defined. And then we generally use our right hand rule in order to figure out the direction. But in a more sophisticated class, like a quantum mechanics class or an advanced mechanics class that you've taken, yeah, you actually have to work with the components. Okay, it's a great little mnemonic, though. It doesn't work in spherical or Cartesian coordinates exactly this way. You have to add some extra terms. They're referred to as metrics. Okay, because if you think about it, in spherical coordinates, you don't have lengths, you have angles, right? So you have to do something so that every derivative that you take is a change of that variable with respect to a length. So you have to multiply by some other lengths in order to do that. Topic for another day. Okay, so why do I bring up cross product? Because I'm hoping that at least 2 people in your physics career have told you that angular momentum is a cross product. And if that's what we're going to talk about in a hydrogen atom, well, we better have that angular momentum cross product technique figured out pretty well. And it is defined as R cross P. It's not commutative. That's completely different from P cross R. Truthfully, the magnitude's the same, isn't it? What's different if you flip the order of operation is you flip the direction, okay? And so if right-hand rule says P cross, or R cross P is this way, then P cross R is going to be the other direction. But evaluating the determinant, just to remind us of those 6 terms, and you can see there are 6 terms here. I've just kind of grouped them as you would get them out of the determinant. So if I'm looking for the I component right here, I take YPZ. That's why I wrote that. And then I subtract off ZPY. Okay, and I wrote them in this order. I always put the direction, the coordinate first and the momentum later. Remember, these 2 guys commute with each other, so I could have written them in either order. Z and PY, order is irrelevant. They do commute. Okay. The only thing you have to remember when you're evaluating determinants, and it's often a mistake I make, this middle term here, that's always a minus J. Okay, that's the one. If I make a mistake in evaluating the determinant, it's probably because I forgot to do this. Okay, and then you cross out the J, and you get XPZ, and then ZPX. That's why I wrote right there. And then, of course, the last one is when you cross out the K column and you get this guy. And so that means, I guess, this is the X component of angular momentum. This is the Y component of angular momentum. And this is the Z component of angular momentum. And so I've just written out what those components are. And I took this guy right here, And you can see I flipped the order. It became ZPX minus XPZ because of that negative sign. Okay, so I've written out each of the components of angular momentum. And this could be the angular momentum of, say, the electron moving around the nucleus and hydrogen, just so it's clear what we're talking about. And I just wrote them out and reminded you what each of the momentum operators were, each of the components of the momentum operator, just taking the derivative with respect to the particular component of momentum we're looking for here. So that's what's going in. Let's see, that goes right there, right? And this goes right here. And that's what you're doing in each of these cases. And so, while they look like variables, remember they're operators. It means you're taking these derivatives. Okay, let's push on that a little bit more. There's an eye chart for you. Let's ask ourselves the question now: do components of angular momentum commute? And you can see after this line of, this would be on the whiteboard, I guess, but boy, it would take me forever to write this out, and I'd probably make multiple mistakes. But the bottom line is angular momentum components, as we just defined them on the previous page, and I wrote them again right here, just in case you don't have them memorized yet. And then I also brought our canonical, I'm probably breaking up right now. So I'll just hold for a second, see if I come back. I also wrote the canonical commutation relationship between, say, x and momentum in the y directions operator, okay? And I just wanted to be clear about what this would mean, the component of, and I wrote x as opposed to y, and I should tell you, your tutorial will have you check, I think, zx, so instead of XY like I'm doing it here, but you're basically going to be doing this same bit of mathematics. You don't have to do it in as much detail. When Griffiths does this example, he does this in 2 steps, I think. For me, that's a little bit quick. And so I want to make sure that you see where this is coming from. And all I did is I said, well, LX is this. So there it is. There's my comma right there that I just kind of drew over, and LY is right there. Okay, and so that's what I did. And so what we said is that's the first thing times the second thing. So boom, boom, like AB, and then minus BA, right? The second thing times the first thing, and you swap the order around. Okay, the good news about algebra is once you got these rules about order of operations and all that, it's a distributive property. It works for operators too. You just have to be a little careful on order, because sometimes order matters and sometimes it doesn't. Sometimes things commute, sometimes they don't. So I tried to be very systematic here. So if you look, my first term is this guy multiplied by that, and then my second guy multiplied by that with the negative sign. And then I did that for the second one too. So the second one, it was that multiplied by that. That's what I'm doing right here. And then the negative sign with the negative sign. So minus, minus, that multiplied by that. Okay, so that's the first and the second terms. And you can kind of see where we're heading here. Then I'm going to distribute one more time each of these guys. And so I got 1, 2, 3, 4, 5, 6, 7, 8 terms again. It's a pain, but that's all we're doing. Okay. And then I looked and I said, once I've got those, so this, you see the first one is those two. The second one is this multiplied by that. And that's what that guy is. Once I did this and got all 8 terms here, 1, 2, 3, 4, 5, 6, 7, 8 on this row, I looked and I said, are there any here that I can turn into a commutator, because it's the same things just flipped in order with a negative sign? And if you look at this guy in the red box here and this guy in the red box, that's YPZ, ZPX, and this is ZPX, YPZ with a negative sign. So I grouped those two together right there. And then I did the same thing for the two in the green box. It was positive ZPY XPZ, and this is minus XPZ Y ZPY, and that became that guy right there. And the other two just follow on. You can, let's see, this, I can find them, I guess. Always look for the positive one. There's the positive one right there, which is that guy. And where's its negative companion? It'd be ZPY. Its negative companion would be that guy. And so that became that. And then the two that are left that I haven't done anything with that I just now guess underlined becomes that guy right there, doesn't it? Okay. Why'd I write them like that? Well, I think this guy can be written as a commutator, isn't it? That. AB minus BA, right? Wrote it as a commutator. This guy I can write as a commutator. This guy I can write as that commutator. This guy I can write as that commutator. And then the question is, well, what are these results using the canonical commutation relationship up here at the top? Well, I look at this and I go, all right, well, do I have oh, look at this. I got a Z here and I got a momentum Z here. Those two don't commute. So this one must not be zero. Okay, let's look over here. I got a Z and I got a momentum Z. Those two don't commute either. So it does not commute, those first two. But now look over here. I got two Z's and an X and a Y. Those all commute, don't they? So there's no way order could matter there because we said if this is Z and this is a derivative with respect to X, they commute. The order doesn't matter. If this is a Z and this is a derivative with respect to Y, they commute. The order doesn't matter. Zero, right? Same thing for this last one. Okay, I got X and Y, and I got momentum with respect to Z in this case. Okay, again, those commute. The difference between AB and BA is nothing there. So all I'm left with is those guys plus zero. And you see what I craftily did here? Since Y and PX, they commute, why not just bring them outside the commutator and leave the two parts, the two things I've circled here that don't commute inside the commutator brackets. And I did the same thing for this one right here. I left the Z and the PZ inside, the things I circled, and I factored out X and PY, the things that do commute. And of course, 0 plus 0 over these two right here. So while it started out being a pretty complicated thing, the question is about the commutation between angular momentum components. The answer is no, they don't, because these two are non-zero. And I use the canonical commutation relationship right here. That's minus IH bar. I did the same thing right here. That's minus IH bar, but in the other order, right? You got to be careful. So this one would be minus IH bar. This one is plus IH bar because it is in the order position momentum. Position momentum is plus IH bar. Momentum then position is minus IH bar. Okay, but then two different components of momentum. And then I guess the last thing I did is I said, well, I can factor out the IH bar, which switches the order of these two guys because this is the positive one. So it became XPY minus YPX. And lo and behold, when I got to that result right there, I went and I go, XPY minus YPX, son of a gun if that isn't the Z component of momentum, right? And so you see, again, a cyclic sort of relationship between these momentum operators, don't you? Angular momentum operators. You can see that LX, LY goes to LZ with an IH bar, doesn't it? Okay. And as I said, you're going to go ZY. It hopefully shouldn't surprise you that the pattern would be ZY goes to, I'm sorry, ZX goes to Y, just like YZ goes to X. And so one of the worksheet problems has you verifying that. You don't have to go through every step I went through right here, but you should go through enough of them so that you can convince yourself that when you put Z, the Z component of angular momentum operator and the X component of angular momentum's operator, out at the end pops the Y component. All right. And so that's the deal. And that's actually the second problem on the tutorial for angular momentum. There was a lot there, huh? That was, yeah, that's certainly about as bad an eye chart as any slide you can do, but hey, that's what I wind up grading when you turn stuff in. So I feel your pain, believe me. Remember we talked about generalized uncertainty principle back in chapter 3, because this was a bigger thing than just, let's see, we did position, uncertainty in position, and uncertainty in the X component of momentum, right? Only the X component, not the Y component of momentum now. We said that has to be greater than or equal to H bar over 2, for example. And I made the case that, there were going to be other operators that we're going to come into contact with that we might have to use this generalized uncertainty principle in order to figure out what the uncertainty answer is for those two. And just to remind you what we did for position and the momentum component in the same direction as that position. Okay, we use the canonical commutation relationship because it's right in there. So right in there, I jammed in X and P, and I realized the commutator of XP is IH bar. The I's cancel, and sure enough, I got H bar over 2 squared. Take the square root of both sides and recover what you've probably known since your modern physics class. But now, let's think about uncertainty for what we just showed, the X component of angular momentum's operator and the Y components of angular momentum's operator. And so A and B here become X component of angular momentum, Y component of angular momentum. Okay, and so I put the commutation of those two operators, and we have a rule now, I guess, for all these angular momentum components that right there is going to go in place of there. Now, I did two things when on the previous slide. This was just a constant, right? And I don't want you to forget there is an expectation value right there that we showed had to be there. But when it's a constant, the expectation value of a constant is just a constant. So I was able to drop that expectation value, that averaging, if you will. I mean, that's what an expectation value is. It's the average of the measurements that you'd make if you had an identically prepared system and you made the measurement multiple times on, say, 100 identically prepared systems, you would get that average. Can't do that here. I have to actually keep the angular momentum as an expectation value, as if I was to measure for 100 hydrogen atoms what the Z component of angular momentum is, that would be a number which is the average. And you've seen how to do that with operators and vectors as well to calculate that. 2.73, was that the number? I forget what it was on the homework. Some weird number like that was your expectation value when you did this with matrices. But the two constants, I guess, I couldn't bring outside, and the I's cancel, of course. And so I've got, and this is all squared because that's squared and that's squared and that's squared. So I got H bar over 2 again, which looks a little familiar when I'm finding the uncertainty principle for these two components of angular momentum. But it's, in addition to being related to H bar over 2, I also have to get the expectation value of the other component of momentum that's missing. Okay, and so this is an application, and you could do it with Y and Z, you can do it with X and Z. You can figure this out and find the uncertainty relationship. Apparently, if you're in the laboratory and let's see, you want to measure these two guys, well, if one's too big, then the other can be allowed to be pretty small, but they're both dependent on the expectation value of the third component. So they're interrelated. As you make a measurement on one component of angular momentum, you lose the ability to measure at least one or the other, and maybe both, depending. I guess you wouldn't lose both if you looked at how those things are. All right, but here's the next question. Angular momentum squared is a question. What about the magnitude of the angular momentum? Does that commute with the individual components, for example? And so that's the next question we have to ask here today. And remember, if I'm trying to get the magnitude, Pythagoras in 3 dimensions, I guess is what I always call that, although that's very inexact. It's just the square, sum of the square of all the individual components. And of course, I'm probably breaking up again. I'll just slow down for a second. What we often do is take the square root here, but we're not going to. We're just going to leave it as L squared. We're not going to find the magnitude. We're going to find the magnitude squared. And again, what I brought this forward in case you don't have them memorized. Although this one's probably memorizable if you stay in the cyclic order. Okay, Y, Z, X, the same cyclic order I talked about when doing cross product, right? Z, X, Y. It always is positive IH bar. times the missing component. Okay, if you went the other, if you flip these two around, it would be minus IH bar. So there are three more commutation relationships between the components that I'm really not talking about. But anytime you flip the order, you just inject a negative sign. Any event, so I want to find the commutator between an L squared operator and a component, right? So what did I do? The first thing I did is I said, well, L squared is just this. And so I used a distributive property here that hopefully makes sense. I took the x component of L squared, this term right here, really, x component of the angular momentum squared with Lx. And then I did the same thing for y. And then I did the same thing for z. And I just kind of dropped this. I'm hoping that's obvious that those would be zero. Okay. It's the same component. It's sort of like saying, what's the commutator of px? Well, it's itself. Okay. And we're going to talk about what derivative might be associated with an angular momentum operator when we come back on Friday. You might guess it'd be a derivative perhaps with respect to theta or phi. And you'd be sort of right. You just got to put those trig functions in that make the spherical coordinate system harder. And maybe if we stay with the z component, we can avoid some of that. We'll get back to that on Friday, but I'm hoping you realize that's zero. And so that's zero for the same reason. And so I think what I did is I wrote out what this should be. And I did something that's kind of wacky, but if you think about it, it is what we do when we're doing like unit analysis and we multiply by one, and one might be, oh, here's an example of one. And I watch my 112 students doing this all the time, incorrectly, unfortunately, in many cases. 100 centimeters is 1 meter. And so we multiply by one in order to get the result we want if we're converting from, say, meters to centimeters. Okay. Well, in this case, if I add and subtract this, two things that are equal, which I think I've done here, I subtracted and then I added the same thing, it accomplishes exactly the same thing for me, because this and this is that commutator, right? I just spread everything out. Ly squared times Lx, and then of course minus Lx, Ly. And then I did the same thing for the next one, okay? And I zapped that thing in the middle because I needed it. In the same way, when you're doing unit conversion, you need to multiply by one. So in this case, I added zero to these terms. It may seem like a strange thing to do, but if you look, rearrange those things, what's that? Well, factor out the common Ly, and what I would just be left with then is the commutator of Ly Lx. And so that's why I did this little add add zero game. And then if you look at these two right here, okay, I factored out the backside. See right here, I factored out the backside right there, those two pieces. Okay, I'm left with the commutator of Yx. And by adding zero in here, I did exactly the same thing right there, brought the Lz out front, Lz Lx minus L, Lz Lx minus the second here, I factored out the front, Lx Lz, boom, commutator Zx, and then this term right here, factored out the z out the backside, and I have what's left, Lz Lx Lx Lz. Isn't that fun? Okay, and so good to go here, I guess. And then I used these relationships that I brought forward about the commutation of the individual components of angular momentum. And so I wrote this guy right here, that was Yx. I got xy is plus IH bar omega LZ. That's why I wrote minus IH bar LZ. Okay. And then I did the same thing for this. This is Yx minus H, let's see, Yx again. Wow, look at that. That went that way. And then I went Zx, negative Zx, nope, Zx is positive, IH bar Ly, and then ZX, which, yep, gets the same thing. And what I notice is those two guys are exactly the same, and those two guys are exactly the same. In each case, one's positive, one's negative. They add to zero. And so, unlike the individual components of angular momentum, the angular momentum operator squared, it does commute with the individual components. Okay, in this case, L squared is compatible. I showed specifically it's compatible. It does commute with the X component. And replace if you replace this with Y, you can show it's also true for Y. If you replace this with Z, you can also show it's true for Z. Okay. Yeah, I do want to mention something. When something doesn't commute, like when I found the uncertainty principle for it, one of the things we said along with not commuting, in addition to having an uncertainty principle, we said that there's no states that are simultaneously the eigenfunctions of these two things that don't commute. Okay, so if they don't commute, they don't have a common set of eigenfunctions, and so that's what we call it. We call them incompatible. Okay. However, L squared is compatible with a component of angular momentum because it commutes with it. And because of that, there is no uncertainty principle between L squared and any component of L. I wouldn't be able to do this because that commutation would go to zero. So there is no uncertainty principle for those things. But we can probably find simultaneous eigenfunctions that would work for an eigenvalue eigenfunction equation for both L squared and LZ, for example, or L squared and LX, or L squared and LY. Okay, there should be a common set of eigenfunctions. And it would be really neat if that eigenfunction set was exactly the same thing we were talking about for the hydrogen atom's energy, or that would be extremely helpful. We'll see if that happens on Friday, and as you may know, it does. But for right now, all we're saying is L squared and LZ could have the same eigenfunctions. All right, and just to make sure we're clear what I mean by an eigenfunction, there is some eigenfunction here, F. It could be psi. It could be some other math function. I was looking back at my notes when I took quantum mechanics at Hopkins. We used U for some reason in this case. I don't know. That was just the textbook we were using. Okay. So there's L squared. And it is possible that when I do one of the components of angular momentum, I'm picking Z because it's a convenient one. And I think you'll agree of the spherical coordinates, it's the one that's the simplest, has the same eigenfunction. Notice, however, we're saying the eigenvalues are not going to be the same. They're going to be different. Okay. And so that's what I mean. This is the classic eigenvalue problem that you've been working on with the operators L squared and the Z component of L. So angular momentum squared, the Z component of angular momentum. And we think these guys should have a common set of eigenfunctions, but not the same eigenvalue. Okay, so we're going to use a technique to solve these eigenvalue problems that was similar to what we did when we did the simple harmonic oscillator. We had raising and lowering operators, you may remember, defined, and they were kind of useful because they allowed us to come up with the eigenfunctions in a fairly straightforward way. We're going to have a raising and lowering ladder operator again for angular momentum. And here's how we're going to define the raising operator will be the X component plus I times the Y component of angular momentum. And we're going to define the complex conjugate of that to be the lowering operator. Okay, and remember what we said about the commutation between the components of angular momentum right there. And so one of the questions, okay, we're always going to ask ourselves is, when we define a new operator, does it commute with the things we've already got, like the Z component of angular momentum in this case? And so just to check it out, I did that. I said, all right, LZ on LX, and I used the distributive property again right here, right? So LZ on the X component, on the real part of it, LZ with the Y component of it, and I brought the I out front because it's a constant. And I think, let's see, this guy right here was that, was that. And this guy right here, zy, was that with a negative sign. Okay. And so I've got I times minus I. That just becomes plus again. Yeah, it flips the order then, though, doesn't it? That becomes the real part from here. And this is the other part. The y component becomes the complex part, the imaginary part. But look, I recover L plus with H bar. Okay, so the answer, I guess, is no. The z component of angular momentum doesn't commute with this thing that's the raising operator. And quite frankly, I wouldn't have expected to, because neither the real nor the imaginary part commutes with LZ, so I wouldn't expect the result to either. But I do get this kind of simple result here. And if I'd gone with the lowering operator, I'd have found the exact same result, except I would have found H bar times the lowering operator is what I get at the end. Okay. Now, I think it is true, and I don't know why I didn't prove it. Why didn't I prove it? I don't know. I'm hoping it's fairly straightforward, I guess, because L squared does commute with both Lx and Ly. Well, then you would expect L squared to commute with the raising operator and the lowering operator, because it commutes with each of the things that make it up. And so that is true. All right, one more thing, and then we'll call it a day here. If we're looking for these simultaneous eigenfunctions, we're saying that, well, this is true. It should be true that if I take the raising operator, okay, and operate on that function, I should get the eigenvalue times the raising operator operating on that function. And I think you'll see that if you do that, it does indeed happen, because this guy right here, we said would be the eigenvalue times the function, the eigenvalue times the function. Since it's a constant, I can just bring it outside. And sure enough, I have that. So if L squared has as its eigenfunction f, it's also true that the operator L squared could have as its eigenfunction the raising operator times f. And right below it, I said the same thing for the lowering operator, okay, which hopefully makes sense. And so the raising and lowering operator times f is also an eigenfunction of L squared with the same eigenvalue lambda that you had for the initial eigenvalue equation if the eigenfunction had just been f. Now let's see what happens with the z component of angular momentum, because here's where the fun starts, I guess. If I was to take and do exactly the same thing, instead of f, I was to replace the eigenfunction with the raising operator times f. Well, let's see, what would that mean? That would mean Lz on the raising operator minus the raising operator Lz. Okay, what did I do right there? And then I get the raising operator times Lz. So what have I done? Doesn't it look like I did exactly what I said I did before, by just inserting a 0 right here on this slide? I think I did exactly that same thing. I got plus z, one with positive, one with a negative. I didn't change it. I added 0 right there. But what I did construct for myself right here was a commutator between Lz and Lx. Sure, I added and subtracted to make it 0, but what I got was that, and then I got that as the leftover piece. Well, what did we say that was just a second ago? Just a second ago, we said Lz commutating with L plus multiplies by HL plus. Okay, and then I just brought that forward right there after I said, okay, well, the result of Lz operating on f is just mu times f, the eigenvalue times the eigenfunction. And so now I factor out this guy, factor out this guy, because mu is just a constant, right? What it looks like is if LZ operates on the raising operator times the function, instead of just operating on the function where I got an eigenvalue mu, when I do that with the raising operator, I get the same eigenvalue, but I add on h bar because of this term right here. There's some mathematical fast and loose right now. It's pretty rigorous, but you know the idea of adding and subtracting the same thing to create a commutator might be a little bit. It wouldn't be an obvious thing to do, I guess, but it works. And just to be clear, and I won't go through it in the same detail, but if you do the same thing with the lowering operator, what it does is subtract h bar from the original eigenvalue of the angular momentum operator z component. Okay, so bottom line, and I'll let you go. L plus minus operating on F is also an eigenfunction of LZ, just like F was an eigenfunction of Z, with a new eigenvalue that either raises the eigenvalue by H or lowers the eigenvalue by H, depending on whether or not you're using the raising operator, in which case it increases the eigenvalue by H, and if you're using the lowering operator, it decreases it. And you should remember when we did the simple harmonic oscillator, it had a very similar function, right? It either took the eigenvalue and it either subtracted h bar omega to the energy eigenvalue, or it added h bar omega to the energy eigenvalue from the initial value when it was 1, which was just, I guess, h bar omega over 2, right? And so when you use the raising operator to get the next eigenvalue up, you would add h bar omega, and that would get you 2. If you did it again, you'd add 2 h bar omega, and so on. We're doing exactly the same thing with angular momentum here, but you can see we're going to add not h bar omega, but just h bar to the angular momentum's eigenvalue. All right, I've gone enough. I actually took longer than I thought it would, but we'll definitely won't keep you late here today because you've got a lot of other things to do. Shortly after, I'm going to stop the share here. Shortly after, I'll be posting the exam. Looks like we've got a lot more people. Since we've got a lot more people, I'll just show you one more time where the exam's located. For those that weren't here at the start of class, let's see. Chrome assignments, and if you go to our Canvas page, there's the assignment, okay, which is where you'll upload it, okay. And if you're looking, internet connection unstable, if you're looking for where the actual exam is, it is right after scattering module, after the chapter 3 formalism module. It's sitting right there. There's midterm 2. I'll make it active, and it's active. It's published right now, and so you can download it anytime you want. I still will have office hours at what's become a normal time, 3:30 today, for questions on homework 7. I think homework 7 is something you probably want to be sure that you can do prior to starting the midterm. And as I said, later on today, I will post the solutions to homework 7 so you can see how I did it, because I think those example problems, as well as the example problems in chapter 3 and the scattering section of chapter 2, should be valuable resources. Should be valuable resources helping you complete the midterm. 3 questions. I think what I decided was a 25, a 45, 25, a 40, and a 15 pointer. So that middle one, the second problem, is the longer one. You should probably be spending most of your time on that. Any questions before we call it a day here? I said I wasn't going to go long, and now that I look after I started talking there, I went way long. Stop the share. Last chance for questions. Hey, good luck on the final. Remember to get it uploaded by I'm sorry, not a final, midterm. Get it uploaded on Canvas by Friday morning. We'll talk to you then.